Okay. Okay, so vector spaces. And we'll talk about special kinds of functions as well. Those functions that you denoted by the letter F previously in calculus, functions that took you from some set that you called domain to another set you called image, and you denote it like this. Okay, for example, y being x squared, that was one of those functions. What did it do, that function f? It took a number x and squared it. Okay, so that was a function. Okay, so this time around, we'll also talk about such functions, but we'll restrict our attention to what we'll call linear transformations. Now, you've seen linear functions before, of course, like say from calculus. Can people remind me what a linear function is and what makes a function linear to begin with? Okay. So now here on my screen right now, you see one linear transformation, an example of a linear transformation, something that you might use in some game application, for example, okay, or computer graphics imaging or an imaging application. Okay, you take some object and you transform it in some way. For example, the way this smiley face is transformed, this transformation will turn out to be a linear transformation. But first we need to define what we mean by a linear transformation. Okay, so first, please remind me, what is a linear function? What's a linear function? Okay, so
a procedure that accepts some input and performs some processes and then produces some output.
Okay, so y equals x squared. It takes some input, and did you say it forms some hypotheses? Is that what you said?
It performs some processes.
Some processes. Okay, let's let the process be square the number that you receive, and out comes another number y. Is this a linear function? Okay, so is this function linear? 2 times x.
Yes.
Okay, why do we say that it's linear?
Because it's like increasing at like a constant rate, where it's like the rate doesn't change.
Okay, so okay, so vector spaces, and you're saying something like, if I multiply my argument x here by some constant number, out comes this constant times f of x. Is that what you're saying? First of all, what did I just write down? I wrote down the following. When I apply my transformation to any argument that's scaled by some constant, let that constant be, I don't know, like 3, okay, then it is the same as if I were to apply that transformation f to my original argument, and whatever I got out on the other end, I took that and multiplied that by 3 at the end. Right? Does that make sense? Did that, just what I said, make sense? So I'm claiming that f of 3x, which is what? What does it mean to write f of 3x? Okay, well, let's take this function here, which is my f. Let's take this function, which is linear, because I don't want to confuse them. 3x, and take that argument 3x, and what does f do to it? F multiplies the thing by 2. That's what the effect of f is. My claim is that this is the same as taking f of x and multiplying that by the constant 3. Is it the same thing? Well, you tell me, what is f of x? F of x says what? Here's what f of x says. Take anything, take that x and multiply that by 2. This is what f of x says. Right? So, but these are equivalent because we know how to multiply in numbers. This evaluates to 6x, and so does this evaluate to 6x. So these are clearly equal to one another. So apparently, whether I take the argument and scale it first and then apply my function, or whether I apply my function first to the argument and then scale it, that doesn't matter. The result is the same. That's what scaling means. Notice that this does not hold for the quadratic function. That's not a linear function. It's not the case for this. Let's make this green. For the green function, for this, let's call it g. G of x being, what is it, x cubed. It's not linear because g of constant times x is not equal constant times g of x. Okay, that is not the case. And people give me an example. So take c again. Take c. What did we have c here? Let's take 7 just for g times 7x is not the same as 7 times g of x. Okay, what is g times 7x? G times 7x is 7x squared. Well, let's talk it squared so that I don't have to compute too much. What is 7 times g of x? This is 49x squared. What is 7 times g of x? That's 7 times x squared. Is 7 times x squared the same as 7x squared? No, these do not equal one another. This is not a linear function. A linear function will always scale linearly when you scale its input linearly. That is, when you multiply its input by a constant, the output will also be scaled by that constant, will be multiplied by that constant. It is also the case that a linear function will take, when you take 2 arguments to the linear function, let's call them x1 and x2, what comes out is this, the sum of the transformations of the arguments. These 2 properties here, collectively, are what make the function linear. Okay, what did I just write down? Is this true for my blue f here, for this f? Yes, it is true, because 2 times x1 plus x2 is the same as 2 times x1 plus 2 times x2. This is my function f, same function f, that doubles its input applied to this argument x2. This is the same function f applied to its argument x1. Their sum, the result of summing these 2 is exactly the same as when I were to sum up the arguments first, and then applied f. That is, what is f? F means multiplied by 2. That's what f is, multiplied by 2. So you sum the argument first, sum the arguments first, and then apply f, or apply f to each argument individually and sum those up. The result is the same. That's what makes a function linear. Those 2 properties are necessary and sufficient to make the function linear, according to our definition. Now, of course, the input to our function, now these are simple examples, the inputs do not have to be numbers. In fact, in our first example, the input was a smiley face. And we claimed that this is somehow a linear transformation. Now, we, of course, have to check every time somebody claims that their transformation is linear, we have to check these 2 properties here. That's scaling the input. So here's some argument to the function. Now, this time t for transformation. This t plays the same role as what f played in our usual functions from calculus. Like this one, f of x is 2 times x, one of the simpler linear functions from calculus. So it was denoted by t for transformation in general. The arguments do not have to be numbers. The arguments can be smiley faces, whatever. Other functions can be arguments. So what does it mean to linearly transform something? Well, if you take any argument from the domain to which t is applied and scale that argument, what comes out on the other end as a result of applying t is this. That is, you apply t to the argument first and then scale it. So here's an example. Here's my v. V is the original vector. Let's call it a vector. Okay, it's just a pair of numbers. The vector is simply on a plane is just a collection of 2 numbers. It's a pair of 2 numbers where the order matters. That's all there is. Think of it as coordinates in a plane if you'd like to think geometrically about it. Here's v. You apply t to it. This is t times b, this piece that I'm drawing right now. So let me see if I can, t times b. Now you stretch v 2 times. Take twice you get to that purple vector here. You see the purple vector, this one? When you apply t to that purple vector, you get right here. Okay, according to this t, apparently this t is such that applying t to twice v gets you to this purple vector, which is the same as applying t to v first, and then whatever you get in the output, stretching that one twice. The result is the same. How about for the sum of inputs? Similarly, if you have, this is your v, this is your w. Okay, what's their sum? What's the sum of v and w? Okay, this is what we're in. So here's the sum of v and w. Do people remember how to sum up vectors? So if you have forgotten how to sum up vectors, okay, so the vector is, we'll usually write them down in columns. You may have written them down as coordinates like that. We'll write vectors like that in columns. Anyway, how do you add up two vectors? Here's one vector, here's another vector. What's the sum of these two vectors on the plane? Do people remember how to sum up two vectors?
Yeah, the two vectors have to be like the same dimensions, and they just like add the coordinates of one with the same coordinates of the other one.
Yes. So if v is some vector like 317, for example, and u is another vector like 521, okay, their sum, okay, you can draw these. You can imagine if you geometrically take one of these vectors, let's say you take the red vector, and take its tail and apply it to the tip of the other vector, just parallelly move it there, and wherever that tip ends up is where the sum of the two vectors will have its tip. And the tail of the sum will start at the intersection of u and v. In fact, all these vectors that we're summing up here, they all begin at the origin. So here's some origin is there somewhere. Okay, the vector, this vector that is the sum, its coordinates would be 5 plus 3 and 21 plus 17. That's true. What you just said, I wasn't going to mention it yet, but it's correct. If you have the components of the two vectors given, how do you find its sum? You just simply add up its components, and that will be the sum vector. That is correct. But let's think about it geometrically for now. So this is how you add those two vectors up. What does it mean to multiply a vector by a number? So this is v. Okay, what is 3v? 3v is just simply stretching that vector 3 times and keeping the direction the same. What happens to the coordinates? Let's say v had coordinates like, I don't know, 2, 7. What is 3v? You just simply scale each coordinate 3 times 2 and 3 times 7. That 621 vector is 3 times v vector. This is 3 times v vector. You can imagine it as something that's stretched in the same direction. Okay, they both kind of, this is kind of shifted. They should both be on the origin. This is v, this is 3v. Okay, you can draw them in the same line. They will be on the same line. Of course, if you multiply v by a negative number, you'll still stay in the same line, but you will reverse direction here. Anyway, back to the point. So I'm assuming that people know how to add vectors and multiply a vector by a scalar. If not, please watch those videos. You should watch those videos anyway. But for example, 3 Blue 1 Brown's videos, if I'm not mistaken, has this discussion. It's somewhere in one of the introductory videos. I'm pretty sure he does, although I haven't watched this in a very long time. Okay, so now here's what we want to say. What happens to the sum of the vectors when you transform the sum of the vectors? This red vector here is the sum of the purple. Okay, all right, let me do it more clearly. First of all, what I want to talk about, let's take the red vector. This red vector here is the sum of v plus w. That's the red vector here. Its tip is right there, just as we did here when we remembered what summing the two vectors is. Now I'm applying t to this sum vector. I get somewhere here, let's say, to this blue vector, this blue vector. How is this blue vector formed? Okay, so this is, on the one hand, this is t applied to v plus w. On the other hand, here's the tv. T applied to v is right here. T applied to w is right here. Oh, okay, so no, I'm sorry, this was wrong. This is what I want to say. T is V plus W. This is T, V plus W. Okay, T, that's T. Okay, so I took this vector here, I took this vector, V plus W, and out came this vector. T applied to V plus W is that. Now, to get this vector, this red vector here in this output space is the same as the first transforming T to wherever it goes. This V goes to T of V, is this vector. Where does W go? It goes to T of W. What is the sum of these two vectors? Which is the sum of T of V plus T of W. They're one and the same vector. They're both this red vector, both these red vector. That's what makes this transformation linear. Okay, so it's just an example of a linear transformation. Okay, so please keep in mind, we'll move on, but please keep in mind that what makes a transformation linear is it's meeting these two properties here. That scaling property, this one, and the sum property. Okay, these can be written down as in one line also, but let's just separate them like this. This is what makes a transformation linear. Now, linear transformations come up everywhere. Okay, this is like the most fundamental transformation there is. You've seen them, of course, in calculus. Derivative is a linear transformation. If you've taken multivariate calculus, then you've approximated your transformations and arbitrary functions by what you call Jacobians, by those matrices that were derivative matrices. That's a linear transformation. So locally, that was a linear transformation. Okay, that's just one example. Let's just take another example. Suppose you like these nuts and chocolates is what your diet consists of today. Okay, you just went with nuts and chocolate all day. And you want to know how many carbs and how much fat you've consumed on this diet. Well, suppose each piece of chocolate of which you've consumed X has that many grams, like 8 grams of carbs. From chocolate, you took that many carbs. From chocolate, you took that many carbs. If one piece from not from chocolate, from the nuts, if one nut had B grams of carbs, this is the total carbs that you've consumed. This is the total number of fat that you've consumed, okay? Because each chocolate of which you had X had C grams of fat, and each nut of which you've consumed Y had D grams of fat. That's the total grams of fat. Okay, so, okay, fine, but where's the linear transformation? Here it is. Instead of T, we now have A. Then why is it linear? That's something that I should be asking you. This is the way we write this down. A applied to X. What is X in my case? X is a pair of elements. In the first example, those were coordinates. There was some vector. Here, they're also, it's a pair of numbers. This time, it's how much chocolate and how many nuts you've consumed. My X, the bold-faced X, is a pair of, think of them, coordinates. What comes out on the other side? Well, on the other side comes a vector. Call it B. What are the components of the B vector? First of all, that B vector has two entries. This guy, AX plus BY, that's the first number. That's a single number. That's how many carbs I've consumed. And the other number, C of X plus DY. Okay. So what I have here is I'm taking A, some transformation. Now I'll ask you in a second what would be a good notation for this transformation. A, but I'm applying it to a vector, and out comes another vector, which is a two-dimensional. It has two components. This B and X have two components. But what is A? That's what I'm asking. What is A? You remember matrix multiplication, right? My claim is now that I can write down this matrix, this A, this transformation, as a matrix. This is the important piece of today, one of the important pieces. Okay. This is going to be my A. What happens when I multiply? You know about matrix multiplication, right? This is a 2 by 2 matrix. I'm going to multiply it by vector X, which is going to be 2 by 1 matrix. My question is, of course, what's the output? It's going to be, what's the dimensions of the output? It's going to be a 2 by 1. Yeah, 2 by 1, exactly. What's my x? Well, x in this case has two components. The components are going to be x and y. We denoted it by x and y. Could have been x1, x2, whatever. Let's call it x and y. And out come some numbers. Those numbers are these guys. First component goes right in here. Second component goes right in here. It's the second component, just like that. This A here, this rectangular array of numbers, is now my transformation. So notice what I'm doing. I'm associating the whole rectangular array of numbers, the whole matrix, with one transformation. Applying, what does the transformation do? It applies, just as our functions from before, from calculus. Those applied to numbers, out came other numbers. This one applies to chocolates and nuts, and out come carbs and fats. That's a transformation, and it is a linear transformation. Why is it linear? If somebody asked you to check, why is it linear? What would you check? You would check those two properties here that we discussed, which would make a good exercise to check that this transformation is a linear transformation. So what do you check? If you multiply x by 2, let's say, or any other constant c, what comes out on the other side? This is what you're checking. If you multiply x by c, what comes out on the other side? Does cb come out on the other side? That's what you need to check. When you take the sum of x plus, like, I don't know, let's call it u, two vectors. What comes out on the other side? Does ax plus au come out on the other side? If it does, then I've checked both of these properties. And this is a linear transformation. But let's move on. I want to give you more examples. Okay. Another place, it's a completely different place where it might come up, is ranking web pages in terms of their popularity, something like Google PageRank. Okay, so we have a small example here, but let me skip it for now. I just want to give you a flavor of where these matrices, linear transformations come up in a variety of places, from calculus, from derivatives to economics to Google PageRank, like everywhere in life as we know it. But for now, everybody here has seen systems of linear equations from somewhere in middle school or high school, from wherever it is. So let's just do a little bit of a refresher. Our goal is to have a streamlined way of solving systems of linear equations. We're called Gaussian elimination. So we'll have an algorithm that solves systems in general. But for now, let's just recall what the problem is. What do we mean by solving systems of linear equations? And how do we write them in terms of our new notation? Where do matrices come in? Where do linear transformations come in? What exactly is being transformed into what? Okay. First of all, let's start with some geometric views of these algebraic equations. What does this represent? What is that? What does that represent? So you have something like x, y, z. Or what does that represent? Let's take this one. 3x plus 2y is 5. Let me move this. What does this represent on a plane? 3x plus 2y is 5. What does that represent? Here's a plane. What kinds of x's and y? Here's my x-axis. Here's my y-axis. What kinds of x's and y's would meet this equation? By meet this equation, I mean satisfy this equation. That is, make that equation true. When you plug in those x's and y's, you plug x and y into this equation. For example, you plug in 1, 1. Here's 1, x is 1, y is 1. You plug in that point. This is 1, 1. This is how we'll denote this point. Write these coordinates in a column. It's maybe strange at first. You say, why are you writing this down? But that's the way we'll write it. Those coordinates for that point, 1, 1, because they satisfy this equation. Okay. Not because, but they satisfy that equation. Okay, so what? Then what? What else satisfies this equation? How many x and y's satisfy this equation?
3 x's, 2 y's.
Sorry, one more time, please.
Are you saying 3 x's and 2 y's?
Yeah, 3 x's and 2 y's, exactly. Not. What do you mean 3x? No, actually, that's not true. What do you mean 3 x's and 2 y's?
Oh, I'm sorry, I must have misheard the question. I'm sorry.
Yeah, no, no. I think you were onto something. Maybe you said two x's, and so anyway, is there? The point is like when x is 1 and y is 1. When I plug those two, so when I have this point, this is my x is 1 and y is 1. This point right here. Well, it makes this equation true. Are there any other pairs of x's and y's that make this equation true? And how many of such points are there?
Maybe x equal 3, y equal 2.
X is, sorry, one more time.
X equal 3, y equal 2.
Well, 3 times 3 plus 2 times 2, how many of that is that?
It would be -3, wouldn't it? Like 3 times -3 is -9. Oh wait, no. No.
Okay.
Would it be 4 and 4? 3 times 4 plus 2 times -1.
Okay. Is that 5? It's not 5, but you're on the right track.
Or -2. -2.
No,
2
no,
times -2.
Okay. So how
That would
about
be fine.
something simpler? Can we take something simpler? How about 3 times 3 minus 2 times 2? I think you were on the right track. I think you said 3 times. Maybe I misheard you, but maybe you were saying like 2 times minus 2. Was somebody saying something like that? That makes it still 5, right? So 1, 2, minus 3, somewhere at this point. No, I'm sorry, 3 and my minus 2 right here, this point somewhere. That point is also there. What I'm trying to get to, I don't want to spend too much time on this. There are infinite number. You've seen this a gazillion times in somewhere in high school or middle school. This is an equation of a line, right? There are an infinite number of points that there are an infinite number on the blue line here. Those two red dots on the blue line satisfy the equation. Any point on the blue line also satisfies the equation. For example, this point of the intersection, what would this point be?
5/2, x 0, y 5/2.
Yeah, no, that's that one. That's correct. 5/2. That's correct. That's that point. This point is 5/3, right? Okay, this point. Okay, so it's kind of slanted like that. Yeah, this is like this. This is lower than this. This is less than 45 degrees angle here. But anyway, how did I get these numbers? Well, I know that here y is 0, right, at this intersection point. So y is 0. What should my x be so that 3 times that x is going to make it a 5, and it's 5/3. Okay, so the point is, I know that the solution is going to be a line. All I have to do is pick 2 points, and the line is given to me, right? All I need is 2 points. Those original 2 red dots here, those are the points that I got at first, according to your suggestions. And then I drew a line in between them, and anything on that line is a solution. Okay, so what's my linear transformation? When I write down, so I'll ask you for a second what this is what's going on with this. Now I have 3 coordinates, so I'm living in a 3-dimensional space. But when I write this down, 3x plus 2y, let's forget it's equal 5. What is my linear transformation? What is the form? What is a times x equals b? What is my a? What is my x? Bold-faced x. Notice this is going to be a vector. Instead of putting these diacritics on top like little arrows, okay, where we're just going to make them bold-faced, those are going to be vectors. What does that mean? It's just a collection of numbers. If I'm in a 2-dimensional space, like here, I'm dealing with lines on a plane. Then my x consists of 2 coordinates, 2 elements, x and y here. Those are x and y. What is my a? First of all, what's the dimension of x and y? It's going to be 2 by 1. Outcomes as a result of this linear transformation, whatever this a is, I'm asking you, I guess, what this a is. Outcomes, well, I can view this as a matrix that is 1 by 1, a number. Outcomes at 5, which is my b, this 5. Outcomes a b, which is just one number. It's a 1 by 1 matrix, 5. Okay. What must the dimensions of a be for this to make sense?
1, 2.
Yes, it should be 1, 2. 1 by 2. That is, it must have 1 row and 2 columns for this to even make sense. Okay, what are the rows of it? So that I have this expression. I know how to multiply matrices. I know how to multiply a 1 by 2 matrix by a 2 by 1 matrix.
3, 2. Yeah, 3, 2.
Yeah, 3, 2.
Yeah, it's a row 3, 2, exactly. That's, okay, from now on, instead of writing it down like this, now this will become a strange way of writing this down, right? Our shorthand way of writing down this line, okay? So I can think of it as a line, right? Because here's the blue line. This is a line. Okay, the x's and y's that make up the blue line here are the x's and y's that satisfy this equation. This equation, shorthand way of writing this down is going to be like that. This is another way of writing it down. Okay, this A is a matrix. It happens to be some kind of a smallish matrix, like 1 by 2 matrix, but it's a matrix. It's a rectangular array of numbers. It's just it just happens to have 1 row in this small example, but it's a matrix. That's a linear transformation. Now, what's happening here before we move on? What's happening here? What does this tell me? What is this in the 3-dimensional? Now I have 3 coordinates. First of all, can you give me x, y, and z that satisfy this equation? It's going to have 3 components, x, y, and z. It's going to be a point in a 3-dimensional space.
Would it be 1, 1, 0?
Yeah, 1, 1, 0, for example, would do just fine. So z is 0, x and y are 1. So this point apparently is, okay, so x is 1. This is my x is 1, y is my y is 1, z, this is my z is 0. So you guys see this point right on the xy plane. That is on the xy plane. Okay, how many xyz's satisfy this equation?
Infinity.
And infinity. Can somebody tell me what, is it a line in the 3-dimensional space?
Yes.
Okay.
I think so, yeah.
Okay, so okay, let's look at another point that may be on this that meets this equation, that satisfies this equation. How about let's take a point where x is not x. Let's see what should we do. Suppose z. All right, let's make x 0. So x is 0. So I want to find out where exactly what are z and y. Z and y. Where would z and y be? Now I clearly have some point where x is 0, and y is something, and z is something, right? So something like 2 times y minus 7z is 5. Can I pick such?
Z can be 1. Okay, go ahead.
Yeah, z is 1. Yeah, okay, yeah, please.
Z1 and y is 6.
Y is 6 and z1, exactly.
Yes.
Okay, so that will work. So z is 1 and y is 6. So apparently this point here where x is 0, and now it will become difficult to draw, but you get the idea. Z is 0, so I'm in the zy plane. Z is 1 and y is 6. So apparently, so I have, that's 1 point, that's another point. How about now let's make y 0. So now I have 3x, now I have something like 3x minus 7z equals 5. Is there another point? So can we pick, oh, this should be z, sorry. There is some combination, right? In fact, you can...
Still Z1 and X4, or we can decrease Z, increase Z.
Yes, actually, you're absolutely correct. So we're all headed in the right direction. We want to find like nice integers here for the solution, but I think we can get away with something like saying, let's make z 0 also, and let's make x equal 5/3. I know it's a bad solution, but it is a solution, right? X is 5/3 and z is 0. That satisfies this equation too, right? So now what we have is y is 0, z is 0, y and z are both 0, and x is 5/3. Where is that point? Z is 0, y is 0, and x is 5/3. So that point here. So apparently this point, somewhere 5. Okay, that should be like, that wasn't quite correct because 5/3 is bigger than 1. So I'm having this point. Here's 5/3 somewhere. Now, so we found 3 distinct solutions the point is, like the way we've selected these solutions, I hope people see that these don't lie on the same line. These are not on the same line. Now, maybe this is a bad drawing, but you can convince yourself that you can always find 3 points that are, for this particular example, that are not on the same line, right? My point is that this will form a plane in the 3-dimensional space. Now, I didn't draw it quite well, right? It's hard to draw this, but you see that it's a plane. You can pick 3 points and you can imagine. It's easier to imagine than draw, unless you're good at drawing these things. You can imagine this plane in a 3-dimensional plane, but it's going to be a plane. We're going to call these guys hyperplanes. Hyperplanes. Why hyperplane? Its dimension is 1 smaller than the number of coordinates that I'm talking about. So this plane lives in R3, and it's 2-dimensional. The plane itself is 2-dimensional. It's like a regular plane. It's exactly the kind of plane that we're used to talking about. Right? This is a hyperplane. Now, that's kind of unusual to call a line a plane, but it's a hyperplane because it's a line that lives in 2 dimensions. The dimension of a line is 1. It's 1 smaller than the space in which it lives. So it's a line, it's a 1-dimensional thing that lives in a 2-dimensional space. This is a 2-dimensional thing that lives in 3 dimensions, and that thing we'll call a hyperplane. This is a hyperplane. This is a hyperplane. Okay. So we drew all this stuff there. So I had some space there. Maybe with these squares would have been easier, but we drew them. Anyway, it looks something like that. If I have 2 equations, okay, this hyperplane here corresponds to some equation, like maybe, I don't know, like something like that, to something like that. This other hyperplane corresponds, well, this corresponds to another, this actually corresponds to the XY plane. But in general, you have 2 equations written down like this in 3 variables. You have 2 hyperplanes. In general, they intersect at a line. That line is the solution to those 2 equations simultaneously. So if I was given this equation and that equation, and if I wanted to find the solution of both of them at the same time, I would be looking for this line. Let's do an example on a plane where we actually can draw these things very, very easily. So yeah, just staying with 3 dimensions here for a second. So here you'd have a system of 3 equations in 3 unknowns. What do these correspond to? Those correspond to 3 hyperplanes. You can imagine the 3 hyperplanes in space. Now, can I ask you one quick question? How many solutions? Hold on a second. Hold on. Okay, well, I have to step away for 30 seconds, but can I ask you how many solutions can you possibly have? 1 second. How many solutions can you have with these 3 hyperplanes in 3? So each one of these lines corresponds to a plane somewhere in space, thrown in the 3-dimensional space. How many x1, x2, x3s can you have that satisfy all 3 equations at the same time? I'll be back in 30 seconds, please. Okay, can I have 2 solutions, for example? Is it clear what I'm asking?
So you want to know how many solutions there are for like when the planes intersect, because is that what it's asking for?
Yes, essentially that's what I'm asking. Of course, there is, this is very general. I could be asking for this concrete case, but it's I think it's very difficult just by looking at this to imagine that, to imagine the 3 planes and tell me how they intersect, because you kind of first have to plot them if you want to do it that way. Now we're going to have an algebraic streamlined way of doing this, so we don't have to imagine these planes all the time, because, okay, maybe in 3 dimensions you can kind of imagine if you'd like to, although it takes some effort. But normally you'd have equations like 15 by 15. You certainly can't imagine 4 or more variables. It's just simply, for a human being, it's impossible to imagine. But it's not unusual to have thousands by 10,000 by 10 by 15,000 system of equations like that, not 3 by 3. So what we'd like to do is we'd like to eventually solve these systems of equations that are thousands by thousands by looking first at these small ones and seeing how those ideas carry over to higher dimensions, the ideas involved in solving them. But yes, I guess, to go back to your remark, yes, I guess I'm asking in how many, can you ever have 2 solutions, for example, 2 distinct solutions to this system? Can you have one solution? Can you have no solutions? Can you have an infinite number of solutions? Oh, well, the answer turns out to be that you can have one solution or no solutions or an infinite number of solutions. There's no other way, no way to have like 7 solutions, okay? And here's why, just loosely put. Let's take the first two of these. Those are planes in the 3-dimensional space. In general, well, those planes could be parallel in an unlikely case. All depends on these coefficients, exactly which planes these are. But in general, 2 planes in the 3-dimensional space will, intersect along this line here. So there will be a line that's the intersection. Then the third guy comes in, and in general, again, I mean, in an unusual case, it can happen that this third plane comes in and intersects the first 2 along this line here. That's possible. But in general, it will cut through like that. If you were to randomly generate these hyperplanes, what do I mean by this? These coefficients were like randomly picked, not just handpicked like here, like 1, 1, 1, 2, 5, minus 1, not like that. And then randomly, if you pick those planes, then you'd get a configuration something like that. Okay? Okay, the planes intersecting like that. They intersect at some point here. There's a single point there that's a solution. So that's a single solution. What is that point? Well, it's some collection, x1, x2, x3. It's a single point that we denote by bold-faced x. It's one object, one vector. It has 3 coordinates, these components, but it's one solution, that point. Now, it's possible you have no solution. So for example, if 2 of these planes were parallel, no matter where the third plane is, there's no way to satisfy all of them simultaneously, all 3 equations simultaneously. So in that case, you'd have no solutions. You could also have an infinite number of solutions. For example, here, when the third plane came in like that, this line is what satisfies all of these planes at the same time. Any x1, x2, x3 points that are on this line. Okay, then you have an infinite number of solutions. Or you can have all 3 planes coinciding with one another, parallel. All 3 planes are really the same plane. So for example, this one, x1 plus x2 plus x3 is 4, and 2x1 plus 2x2 plus 2x3 equals 8. Those are the same plane. I've just written down the same set of x's and y's. It's exactly the same, I mean, not x's and y's, but x1s, x2s, and x3s. It's exactly the same x's that satisfy both equations. Okay, those are the same plane. Okay, if you plot them in the 3-dimensional case. Okay, so I think we get an idea of what's involved in finding this. Of course, we don't know how to solve them in general yet, but at least we're getting some initial ideas of what's happening. Now let me ask you this, okay? You've solved this like way back. Maybe you've even forgotten how you did this in the past, but now we'll want to get new insights, perhaps some insights that were not available when you first solved this. Maybe they were. We don't know. So let's just discuss it for a second. Let's start actually just by solving. Now, if somebody asked you to simply solve this, what would you do? Okay, so we want to have 2 different ways of solving this system of equations. Okay, so let me just copy this and bring this over. Okay, I've already copied it here. Okay, so how would you solve this system of equations? Now, let me tell you that what I want to do before today ends, I want to do it in 2 very different ways. Of course, if I ask you to just simply solve it, you'll find the x and y that satisfy both. Okay, I have no doubt. Maybe you need a few minutes, but you'll find them. That's not what I'm asking. Let's just go through the solutions together, and both of my solutions today will be geometric. One solution we'll call the row picture, and the other we'll call column picture, and we'll end up preferring one of the 2 in what follows through the rest of the semester. Let's start with the row picture. Row picture simply means this. I view each row as a hyperplane, as before, as we've been discussing just now, and I'm just simply going to plot those 2 lines. That shouldn't be super complicated, so let's just do that first. I need the xy plane, so here's my x, and here's that's my y, but here's my x, so that's going to be my x, that's y. These are coordinates. Okay, so this is a line, x minus 2y equals 1. Okay, all I need is to, let's make this one blue, and this one, let's make this one red. So let's plot the blue one. 1, 2, let's have these guys. This is the unit of 1, same thing, scale wise, just to make sure. Okay, so x is 1 and y is 0 at this point is clearly on the blue line, right? That satisfies this blue line. What else is on the blue line? How about x is 3 and y is 1? Does that work? X is 3 and y, does that work? Is that on the blue line? Right? Am I correct? So what? So please tell me if I'm correct. Maybe I'm making a mistake. I don't know.
Yes.
Okay. So this, I know it has like slope 1/2. So that's how it's going to intersect here. So if you, by the way, this point, why is it 1/2? If you plug in x 0 and y 1/2, it works just fine. Anything on this line, on this blue line, satisfies this equation. Then I plot the second line. Okay. Then I plot the second line. What is the second line? How about x is like 3 and y is 1? Does that work? X is 3, y is, okay, that was a, okay, so apparently this point is there. What else is there? How about, so please give me another point. So for example, x is 0, then what is y? 11/2. What is that? Like somewhere here, 11/2, that's 5.5. 1, 2, 3, 4, 5, 5, somewhere, oops, somewhere here. So I have this line, right? Do people see this? This is 3x plus 2y equals 11. This one is x minus 2y equals 1. And it turns out that they intersect at this point. So the solution, x equals 1, y equals 3, is a solution. Of course, we write this down as 1, 3. And yeah, that's the solution. So you can check that that's the solution. It does the trick. If you plug in x, this is my x component, small x. This is bold-faced x as a vector. You can call it v if you'd like, but let's call it x. And this is the y component of it. We could have had this x1 and x2 for y, but we chose x and y in this example. Fine. Now, if I were to ask you to find a solution to this, you may have said that, okay, look, like when I first saw these systems of equations, like back wherever it was, I was told that I can eliminate some variables from the two equations. So for example, I have the first equation I'm going to rewrite. Now I notice that I can eliminate x from the two equations. How would I do this? I multiply the first one by 3, okay, and subtract the first one from the second one. What would I get? If I multiply the first equation by 3 and subtract from the second one, what would I get? Do I get this? Right? Okay. So this system of equations here, this system of equations. Yeah.
Yeah, I think it's right.
Okay. So now let's solve this one. Let's solve this one. Let's plot these two guys. Of course, the green line, the first with the green line, which is my blue line here, that didn't go anywhere. Let's use a different color, like purple for this guy. Purple, let's call this purple. Can you plot the purple guy? This is the same as y equals 1 line. It's this line, y equals 1, no matter what x is. Y equals 1 line. You see that the intersection is there for this system? So it's, of course, the solution doesn't change. All I've done is just pivoted this red line somehow into the purple line along this point. But the point is like that I no longer have this line, the blue line, the original blue line. Or rather, I'm sorry, I still have the blue line, of course. The blue line corresponds to the first equation. I no longer have the red line. Instead of this red line, now I have the purple line. So let me give you a better picture so that it's clear. And from the next slide, here's what I have. Here's the original system of equations. This is what we did, found the solution. If we eliminate x from the two equations, we're down to this system of equations. If I plot that again, I get this picture. The point is that the solution hasn't changed. The solution is still the same. So this manipulation of rows, the way we've done it, multiplying one row by a number and subtracting from another, does not change the solution set. Okay, if we had to prove this, we have to argue this more carefully. But from this example, I think you can see it. So here's the change. Subtract some multiple of row 1 from the second row, 3 times row 1 from the second row. You'll get a different picture, different row picture. The solution is still the same. All I've done is like pivoted around some point. That doesn't change. Okay, that's point 1. That's one way of solving the system of equations by looking at these each of these equations as hyperplanes. Now, let me do this. Let me copy this. Now we'll do a preferred way of solving the systems of equations. This is going to be very different, but of course we better get the same result. Now I'm going to take a completely different vantage point. Now I'm going to view this system completely differently. Now I'm going to solve the same system, and I'm going to call this a column view of the system, or the column picture, just as we call that the row picture. It's called the column picture of the system. Okay, what is the column picture? Now let's write this down as A times X equals B. What is A times X equal? What is my A? What is my X? What is my B? Help me out while I'm drawing these axes here. So I'm going to have this axis. I'm going to have this axis. I'm going to draw something. Notice that this will be a completely different picture than the one that I had before. Okay, this column picture will be very different. Okay, so while you're helping me determine what A is and what B is. In fact, let's write this down. A is going to be 1 minus 2, 3, 2. X is going to be just X and Y. Okay, and Y is going to be just, not Y. The B is going to be 1 and 11. You know about matrix multiplication already. So I've just rewritten this system equation in the matrix form. That's just a shorthand for now. But you notice what I can do. I can take this column, and this is the important point. 1, 3 is going to be the first column of A. This is going to be my second column of A. Is going to be, of course, minus 2, 2. If I multiply this by X, because this is what that system says, plus that times Y, it says you better get out this pair, 1 and 11. Let's see what that means. X and Y are some numbers. Okay. Now notice this R2. This is my R2. This is not an XY plane as before. It's very different. It happens to be a 2 by 2. It happens to be a plane, but this is not the same plane as this one. This is a different R2. Let me just simply plot these columns, 1, 3. Okay, so where is 1, 3? So this is my scale. This is 1, 3 is going to be this here. This is going to be my column 1 of A. What is minus 2, 2? Minus 2, 2. It's right here. Minus 2, 2. That's going to be my column 2. This is my column 2. That's the second vector. This is column 2. What is my 1, 11 vector? Let's plot that one too before we go. 1, 2, 3, 4, 5, 6, 7, 8. That doesn't fit. Okay, 9, 10. Okay, it's 11. It's right here. Okay, let's just draw it anyway. I think that's 11. So let's just plot this. This was bad, but you get the idea. I just want to plot this 1, 11 vector. Okay, here's 1, 11. 1, 11. This is the right-hand side. This is B, which is 1, 11, the right-hand side. This is my B. That happens to be 1, 11, what I plotted. What does this system say? What the blue X and Y, what does that mean? What does it mean to multiply, for example, column vector 1, 3 by the blue number X? it says scale the vector, the purple vector 1, 3, which is the column. Scale it x times. What does it mean to multiply by y, the second vector, the second column vector, this minus 2, 2? It means scale it y times, and then add them together. Add them together. That is, notice what this system of equations is asking me. What kind of scaling factors, which scaling factors x and y will lead me to this output vector b? Notice that if I scale it, if I scale this 3 times, scale this 1 time, let's see what comes out. I know the solution to this to be x equals 3 and y equals 1. This is from a previous view, from a row view picture here somewhere. I know that the solution has to be that. This is a different x. So, okay, that was the solution. Well, actually, the solution is the same, x. The coordinates 1 and 3. There, these were the coordinates. Here, they are some scalars by which I weigh each individual column vector of A, matrix A. 3, 1, I know to be the solution, so let's check. What does it mean to multiply this vector, purple vector 1, 3 by 3? Well, it just simply means scale it 3 times. So it's going to be 3, this was 3, so I get up to 9. 11 is 10 is 9. So I end up somewhere there. So this is going to be my, let's make this red. Let's make this red. This vector, the red vector, is going to be 3 times column 1. Column 1, which is 3 times 3, 1. Well, let's make 3, 1 purple. 3, 1. This is 3, 1. And that's going to be 9, 3. Okay, is that right? Column vector, I'm sorry, 1, 3. 1, 3. Are people on the same page? The people didn't correct me when I made a mistake. This was 1, 3 vector. This is 1, 3 vector. Okay, so 1, 3 vector, right? 1, 3 vector, 1, 3. I'm going to get 3, 9. That's my 3, 9. 3, 9 vector. 1 times minus 2, 2. That's just the same vectors. 1 times this vector. It just stays put. Doesn't go anywhere. What happens when I add those two up? How do I add up those two vectors? You can transport this parallelly, whatever, any way you want. But when you do this, when you draw it like that, you end up exactly at the tip of this black vector, which is B, the right-hand side. Do people see this? That it's exactly 3 times column 1 plus 1 times column 2 that will lead me to the output vector B. There's no other combination that can get me there to that tip of that vector. This is a completely different view of the system of linear equations. It is not the same as this hyperplane view, where we changed those hyperplanes, reconfigured them somehow in the 3-dimensional space. This is a different view. This is what's called a column view. Here we view the columns of matrix A as vectors in this case, in 2-dimensional space again. I have a 2x2 matrix here. The columns are 2-dimensional vectors. So I'm adding up some combination. This is called the linear combination of the vectors. Okay. A1 times x plus A2 times y. It's called this vector. This is vector. Column 1 of A. This is another vector. This is column 2 of A. Okay, that's another vector. This is called linear combination, important term, linear combination of A1 and A2 as vectors, as 2-dimensional vectors. These x and y's are scalars. These are just numbers. They're not vectors. These are not pairs of points. X and y's are numbers, and A1 and A2 are the columns of A, like that, written down as vectors. So when I scale up these columns and add them up, I better get the right-hand side, 111. There's only one such mix of x and y can give me 111. when the mix is such that x is 3 and y is 1, only then I can get 111, in no other case. That means that this system of linear equations has a unique solution. And of course, that's what the row picture told me as well. It found a solution. There's a unique solution. Why? Because these two lines intersect in one point exactly. If these lines were parallel, I'd have no solution. If these lines coincided with one another, I'd have an infinite set of solutions. But here I have just neatly just one solution, two lines intersecting in one point, which is the most common configuration of two lines on a plane. Okay, all right. I think we're nearing the end. So so please help me. What did we do all day today? Did we do anything? What happened today? We started talking about systems of linear equations. We want a streamlined way of solving 10 by 10, 20,000 by 17,000 systems of linear equations. We started with 2 by 2 and 3 by 3 examples. We saw that those can be visualized geometrically in 3 or 2-dimensional spaces. And there are two distinct views of those systems of linear equations. One is called the row view, in which we view the rows in the system as hyperplanes and look at the coordinates that satisfy all equations in the system simultaneously. That geometrically corresponds to an intersection of hyperplanes, just like that. We saw that manipulating rows, as we discussed, namely by multiplying any given row and subtracting that multiple of that row from another row, does not change the set of solutions. Didn't prove it, but we illustrated it with an example. We can find the solution to the system by using those kinds of reductions, that is, by eliminating variables. Didn't change the set of solutions. And this one was presumably easier to solve algebraically than the original system, because you had fewer coefficients to deal with. Geometrically, the picture changed in such a way that the solution didn't change, although the planes themselves were reconfigured in space differently. And then, most importantly, we took another view of the whole system, completely different viewpoint. From this new vantage point, which we dubbed column picture, the column picture of the system of linear equations, we now view columns of the transformation itself, of the matrix itself, as vectors in two-dimensional space. And x's and y's are now those coefficients by which we have to weigh the columns, mix the columns up, the columns of A, the transformation, in order to get the right-hand side exactly. In this case, the mix happened to be 3 times the first column vector, 1, 3, and 1 times the second column vector, which was -2, 2. When I mixed those two red vectors just like that, I was led exactly to the output vector B, which was 1, 11. Okay, and that was it. That was all of today. Okay, that like a few sentence summary of all of what we did today. Does that make sense? Does this discussion make sense? So now here, let me tell you, 2 minutes. Okay, all right, what did I just do? I think I closed something. How about now?
Yeah, we see the
Yeah.
Yeah, I see your screen.
Okay, so here's the textbook. I have it somewhere here. Here's the textbook. Where is the textbook? It's posted on Canvas. Where can you access it from? From the syllabus. You go down to syllabus, maybe it's in files there somewhere too, but here it is, the fundamental of matrix algebra. That's your textbook. The reading assignment for this week is the entire chapter 1 for sure. You should read, this book is meant to be read, so please read it and supplement it with the first 3 videos from 3 Blue, 1 Brown, right? So for the next week, 10 days, your reading assignment is the first 2 chapters of this. So it's like about 100 pages of reading. And you have about a week, so that doesn't sound like too much. Although you may have to obviously reread some of the sections to ensure that those make sense, right? So let me stop the video here.